Hello mathematicians. Today we're going to be continuing working with our integration strategies. And we've been recently, how do we integrate when we have something that's definitely using the chain rule? And we're going to have something called the substitution rule, or u-Substitution colloquially. Now let's take a look back at the chain rule for derivatives. We know that if we have the derivative of a chain rule function where we have a f of g of x, where we have a function that's embedded inside another, it's the derivative of the outside function, keep the inside function the same, multiplied by the derivative of the inside function. So as an example, taking the derivative of secant of x to the 4/3, we know that first we're going to apply the power rule, get 4/3, keep that argument, the inside the same, secant, we're going to subtract 1 from the exponent, and we have 1/3. Then we're going to multiply by the derivative of the inside, which the derivative of secant is going to be secant of x multiplied by tangent of x. So that's our derivative of secant of x to the 4/3. We have this outside function, which for us was something raised to the 4/3 power, and we had this inside function, which was secant of x. So chain rule is the derivative of the outside function, keep the argument, the inside the same, multiplied by the derivative of the inside function. Well, going backwards, if we have, let's write it over here on the right, if we have d dx of f of g of x, we know that that's f prime of g of x multiplied by g prime of x. Well, going backwards, if you want to integrate that, take the antiderivative of, and I know that I'm not messing up my notation here, but if we're taking the antiderivative of something where we have outside function prime, the derivative, keeping the argument the same, let's turn that off, multiplied by the derivative of the inside function, it would be equal to the integral on the left side, which that would just be f of g of x. So there's our outside function, our inside function. How do we look for that? Let's take a look at this example down below. Find the antiderivative. So I have, very similarly, secant x times tangent x times the cubed root of secant of x. Now we can rewrite that as being secant of x raised to the 1/3 power multiplied by secant x tan x dx. And I wrote it that way just so that we can very clearly visualize. There's our inside function, secant of x. That's like our g of x. And then we have secant x tangent of x. That's our g prime of x. So we're thinking about, there's this inside function, there's this outside function. Our antiderivative is going to be, now thinking about this, I'm going in, okay, I've got a power function, so I'm going to add 1 to that exponent. It's going to be keep that inside function the same, secant of x to the 4/3, and then times, now checking this, if I take the derivative here, I've got 4/3 multiplied by something gets me coefficient of 1, that's got to be 3/4. And if I check my derivative, 4/3 times 3/4 gets me a coefficient of 1. Subtract 1 is going to get us the 1/3 exponent. The argument, secant, stays the same on the inside, thinking chain rule, and then we've multiplied by the derivative of the inside. So actually, that's our entire antiderivative. And I did plus c because I have an indefinite integral, no bounds. 3/4 secant x raised to the 4/3 plus c. Formalizing this, we are taking advantage of something called the u-Substitution. So frequently, how mathematicians work this. So we use the substitution rule for antidifferentiation. Happens when the chain rule is in play. We're going to replace that interior function with some statement. Now, typically we could say u. It can be any letter, but we talk about in mathematics the u-Substitution. If that interior function is a differentiable function whose range is in an interval and f is continuous on that range, on that interval, then we can rewrite our chain rule as just the integral of f of u du. You're looking for this inside function and the derivative of that inside function. There's going to be this partnership here. Frequently, we can look for something that is grouped by parentheses, or how can we find some inside piece with an outside piece. Let's take a look at a few examples and formalize this practice of u-Substitution. Number 1 here on the left, let me zoom in. I can see that I have 2x times the square root of 1 plus x squared. That nature of the square root, the radical, is it groups an inside piece. I'm going to say that's my inside function, g of x. What I'm going to do is I'm going to replace this. I'm going to say u equals 1 plus x squared. Here's where our u-Substitution comes into play. That's going to give us now 2x multiplied by the square root of u dx. All right, so I can see that's taking one piece. I'm going to rearrange this a little bit so I can see where my derivative of the argument, the inside piece, comes into play. I'm just going to move that around. We still have u and x, though, in this integral. So we need to replace every instance of x with one common variable. In this case, for us, it's going to be u. I'm going to take my derivative of u. So if I do du dx, that's going to be equal to 2x. And I'm going to rewrite this using what's known as a differential. It's going to be du is equal to 2x dx. Oh, here's the nice part. So what this means technically is that when we've taken the rate of change of u with respect to x and rewriting this, we've got the change in u is equal to 2 times x times the change in x. So if we know how much x is changing or what x is, that tells us about the change in u. That gives us a substitution. Instead of writing 2x dx, I can replace that with a u. So my integral becomes, and I'm going to rewrite this with an exponent, u to the 1/2 du. Now we have an integral that we can evaluate. It's easier to look at, it's more simplified, it's just going to be an application of the power rule. So let's integrate, find the antiderivative. That's going to be u, add 1 to the 3/2. Thinking about my power rule, I'm going to multiply by something. 3/2 times something gets me a coefficient of 1. That's got to be 2/3 plus c. And I'm going to replace back sub. So I've got 2/3. U is that 1 plus x squared to the 3/2 plus c. If we check, because it's always important to check our derivatives, the derivative of this, we're going to multiply 3/2 times 2/3 gives us a coefficient of 1. Subtract 1, we have the square root. Multiply by the derivative of the inside, multiplied by dx. So there is our final antiderivative. We're looking for this combination of an inside function and the derivative of the outside. So here's really like our gx, here's our g prime of x. F is our outside function containing that interior g. Let's take a look at the second example. We've got the integral of x cubed cosine x to the 4th plus 2. Now, it might make sense that, well, that's grouped for us. So let's try this. We're going to say u is equal to x to the 4th plus 2. I'm going to take the derivative, and I've got du then, and I'm skipping a step here, be 4x cubed dx. I'm going to look back at my statement. There's the x cubed, there's the dx. Ooh, but there's this extra 4 here. What I'm going to do is I'm going to rewrite my integral. So I've got the integral of cosine now u, because that has replaced the u. And I'm just going to group this. So I've got x cubed dx. You can see there's that x cubed dx. But got to get this 4 out of the way. I'm going to manipulate this. I'm going to divide by 4. So I'm going to have 1/4 du is now equal to x cubed dx. And I can see that's going to be our substitution. Let's go all the way then. So we've got integral of cosine of u multiplied by 1/4 du. Because this is a constant, because 1/4 is just a constant, I'm going to pull that outside of the integral. I can do that because there's no variable there. Let me neaten up. So now we have the integral of cosine of u, which we know is going to be sine of u. Still constant, 1/4 plus c. And because u is x to the 4th plus 2, I can back sub that. We've got x to the 4th plus 2. There's our antiderivative. And we should check it to make certain that we have that accurate. Let's try the next one. Good sub here might be u equals 1 minus 4x squared. That's going to give us then du is negative 8x dx. What I like about this is there's the x, there's the dx. All right, so that part is going to be replaced. Let's make the substitutions now. That's going to give us integral of negative 1/8 1 over square root of u du. Figure out how I made those jumps in there. This I'm going to rewrite using a power. It's going to be u to the negative 1/2, and now that's a statement that I'm comfortable with. I have negative 1/8. This is going to be times 2 u to the 1/2 plus c. And if I substitute back, I've got negative 1/4, 1 minus 4x squared raised to the 1/2 plus c. Let's take a look at number 4 now. So there's definitely a clear interior function. Let's jump right ahead. That's going to give us u equals 1 plus x squared, allowing us du is 2x dx. And I see that I've got that 2 there. I'm going to get rid of that 2 over the other side. So I've got 1/2 du is equal to x dx. And now we'll make our substitution. You can see I'm getting really excited about this. This is going to be 1 plus x squared to the 1/2 power. So it's going to be u to the 1/2 power. I've got a constant 1/2 outside from there. And then I've got a, oh no, that's x dx. That's x to the 5th dx. So we would be left with x to the 4th times x dx coming out of that x to the 5th, because there's our x to the 5th. That's all we can substitute. Let me take care of that. That's going to be du. Now, I can't really pull that out because that's a variable. But we've got u, we're integrating with respect to u, everything has to be in terms of u. We've got u to the x to the fourth, we got to do something with that. Here's where we play with some tricks with our substitution. We have u equals 1 plus x squared. Let's manipulate that, and then we know that x squared is u minus 1. Maybe you can see where I'm going. That's going to give us then x to the fourth is u squared minus 2u plus 1. So we had to have some extra manipulation. We defined u in terms of some interior function. We've got that. But then it wasn't all clear-cut, simply replace. I've got to rearrange some things, manipulate, turn this into something that I can do. So now, let's get the right color. We've got 1/2 integral u to the 1/2 x to the fourth is being replaced by u squared minus 2u plus 1 du. And now that's going to be 1/2. We've got the integral of u to the 5/2 minus 2u to the 3/2 plus u to the 1/2 du. Notice how I distributed that u to the 1/2 in there. Now it's just a power function, and we can do that. We can easily find the antiderivative of that using our power rule. Let's take apart and see what happens if we've got bounds with definite integrals instead of indefinite integrals. Same rule applies, but I'm going to tweak some things a little bit. Make some things when we have, make a change that is a possibility when we have a definite integral. Here on the left, number 1, let's take a look. We've got the integral of, from 0 to 4 of the square root of 2x plus 1. Now you think good substitution might be 2x plus 1. Then we're going to have du is equal to 2 dx. But since there's just a dx there, I'm going to move that 2 to the other side. So I've got 1/2 du takes the place of dx. So my integral becomes square root of u, or u to the 1/2. There's a 1/2 du replacing. What I can do is that look at the bounds here. Our variable, our integral is now in terms of u. Back to the original, this is x equals 4. This is x equals 0. We cannot, put a big no there, write 0 to 4 because we're in terms of u now, and this is x equals 4, this is x equals 0. We need to write that in terms of u instead. Now, if x equals 0, well, u is 2 times x plus 1, giving us that u is going to be 1. So instead of using x equals 0, I can rewrite this and say u equals 1. Before, x is 4. So instead of having x equals 4, I know u is 2x plus 1. That's going to give us u is 9. So I can rewrite my integral, changing the bounds in terms of the new variable. Then it's one less step, so I do not have to back sub in terms of x. I still can back sub in terms of x, but now I can keep it in terms of u. We're going to have 1/2. That's going to be 2/3 u to the 3/2 evaluated from 1 to 9. So I've got 1/3 u to the 3/2 evaluated from 1 to 9, and I can sub that in. I've got 1/3 9 to the 3/2 minus 1/3 1 to the 3/2. So that's going to give me 27 over 3 is 9 minus 1/3. And I can get what that is. So when I have a u sub and bounds, I can change it in terms of the new variable. Try it out. Catch you later.